Yesterday, we sort of wrapped up some of the solutions to the constraints imposed by the second law of thermodynamics in axiomatic formulation of hydrodynamics. And in the process, we saw some intriguing structures, in particular that at least in a particular restricted class, entropy came out to be a Noether term. And then I switched gears to start talking about how we should think about hydrodynamics as arising from some microscopic quantum field theory perspective in a thermal state, and introduce to you the Schwinger-Keldysh functional integral, which I'll review to begin. So just to recap, the Schwinger-Keldysh functional integral is defined by starting with some arbitrary initial state. I have pretended that my initial state is thermal because that's what we're going to be primarily talking about, but everything I say for this, some parts of what I say for the Schwinger-Keldysh construction are quite general. And what you do is you evolve this density matrix forwards and backwards by conjugation with unitaries with sources, or in functional integral language you can think of it as having two sets of degrees of freedom, the right and left, which have opposite decoupled actions in the ultraviolet with correlations built in through the initial state that you've sort of prepared the system in. If you deform this path integral, then the sources you insert would couple this way with the right sources coupling the right operators and left sources coupling the left operators with a relative sign. And much of what I'm saying here is just a mnemonic. You can think of one other way of saying what I'm saying is that the fields live to compute the retarded or advanced Green's functions. You need an I epsilon prescription. And roughly speaking, this distance tells you what the I epsilon is in this contour. Okay? So this distance is physical because if this state was a thermal density matrix, then this imaginary time evolution would correspond to imaginary time evolution by almost beta minus epsilon. But this epsilon is just the regulating part which tells us what the ordering of objects is. And I showed you that you can use this, that the right orders are right operators are time ordered, the left operators are anti-time ordered, to compute any set of correlation functions with a certain set of time orderings and anti-time orderings. Now it's important to realize, and something I was going to say but I don't think I have time to go into, is that this functional integral contour will not compute arbitrary time orderings. It will not compute arbitrary Weitman functions in a quantum field theory. If you want to compute arbitrary Weitman functions, you have to do this forward-backward evolution multiple times. So I'll leave it as an exercise for you to think about it and why that must be true. The easiest way to do it is to just imagine writing down a Weitman function of Heisenberg operators and think of what Heisenberg operators actually mean in terms of evolution. Okay, so what we're after is, suppose someone gave us that story, then we can just compute whatever we want. But what we're after is sort of starting with that system, with some microscopic system, and prepared in some density matrix. But we're not after sort of keeping track of all the details. We want to do some effective field theory. So we want to have the freedom to be able to integrate out a set of what we would consider irrelevant ultraviolet degrees of freedom. The trouble is, in this Schwinger-Keldysh functional integral, we could just say, well, just go ahead and integrate, split phi right into phi right UV, phi right IR, phi left into phi left UV and phi left IR. Just integrate out phi right UV and phi left UV. And then you might say, well, why doesn't it just do what the standard Wilsonian paradigm tells us to do? You write down all possible terms in the low energy theory which are consistent with the underlying symmetries. You can't just do it because, and that's sort of deceptively misleading in this formalism, as someone was pointing out yesterday. The action looks like it's factorized between left and right. But there's correlations buried in the initial conditions, which means when you start integrating out the UV modes, you will in principle and always induce left-right correlations in the action. So the low energy theory will not have this form. It will have this form for the IR modes plus some interaction piece between the left and right IR modes. Okay? And your task is to be able to convince yourself what is allowed for those left-right coupled IR modes. And that's what these folks call influence functionals. And the real question is, what influence functionals are consistent with microscopic unitarity? Because an arbitrary influence functional would not respect microscopic unitarity, and I'll show you one way of implementing it quite efficiently. We'll need something more than just this, because we are going to be doing thermal density matrices. So as I said yesterday, we'll also need to encode not just this microscopic unitarity into the game from first, but we'll also have to incorporate the fact that our system was initially prepared in the thermal state, so therefore it has KMS, thermal symmetry built in. Okay? And so what I'm going to do for the rest of this lecture, and I'm going to apologize because it comes at the end of a long day for you guys, it's going to get steadily technical till the end, but hopefully the payoff will be visible tomorrow. We're going to try to encode the Schwinger-Keldysh constraints, which are visible in the UV, in terms of some symmetry principles that we can then just incorporate into the low energy theory. Okay? The symmetry principles that we'll uncover will be symmetry principles involving some BRST topological structure, and then I'll tell you how to understand this. Okay, so let's start. So first, let me make a very trivial observation, but one that has profound consequences. Suppose you take the Schwinger-Keldysh functional integral that I had 2 slides ago, and say j right equals j left. Then this unitary out front is the same as this unitary out front up to a conjugation. And since the trace is cyclic, you can just bring those two together. And what you get is that the partition function with the two sources set equal is nothing but the trace of the initial density matrix. Okay? But since these difference operators couple to j right plus j left, or equivalently to j equal values of j right and j left, it immediately follows that an arbitrary correlation function of an arbitrary number of difference operators is just 0. Why? Because where you get these correlators is by taking this ansatz and then differentiating with respect to the sources. But the answer is independent of the sources. Okay? Now, if you think about it for a second, this is a rather remarkable statement, because these operators, I haven't indicated their time arguments, they could have been placed at any time. Okay? But if you didn't know where this came from, you'd be very surprised, because someone would come and tell you, you have some quantum field theory, and there's a whole class of operators which doesn't seem to care about what your Hamiltonian was, what your dynamics was, but it had trivial correlation functions. Okay, this doesn't typically happen in a quantum field theory. Of course, there's an obvious reason why this happens here, and the obvious reason is, if you go back to the microscopic picture, it's simply because you're evolving forwards with some unitary and evolving backwards with the same unitary, and that does nothing. Okay? So in the microscopic theory, this nothing is simply the consequence of unitarity of evolution. But in the macroscopic theory, once things have started getting intermingled, you should try to find a useful way to encode doing nothing. And a useful way to saying what nothing of doing nothing is to say that there's a nice BRST symmetry under which these guys are BRST exact, they are cohomological objects, so they don't have any correlation functions. So this is typically true in all topological field theories. Correlation functions of topological operators vanish simply because they are preserved under some cohomological algebra. There's one other, so this statement you can just see. There's one other statement which is slightly trickier to implement, but also true. So let's imagine now that you don't do what I just said. You don't set the sources the same. What you do is you try to start computing correlation functions of average operators, difference operators, what have you. But let's say for some reason you decided to put a difference operator at the futuremost time. What would that give you? It would give you 0 because there's some n plus 1 point function with the difference operator at the futuremost point. But that piece of the contour where you go from the n after inserting n operators to the n plus 1th operator involves evolution forwards by some unitary to insert that operator and evolution backwards by the same unitary conjugated to insert the same operator on the downward contour. Okay? So you can collapse that last piece of the contour again because its u dagger is 1. It also means that you cannot have a difference operator as the futuremost operator in a time ordered correlation function. Okay? There are many ways to say this. The easy way to think about this is that this contour should, it's actually a slightly silly way of saying this, but it's more useful when you go to higher out of time ordered correlators. You should think of this contour as an abacus. An abacus where operator on this end can be slid down freely if it's unobstructed down. Okay? Because out here in a matrix language, this piece of the contour, what I call turning point, is really an identity operator. It's the projection onto the maximally entangled state. So you can either put, if you have a future operator, it can either be left or right. It doesn't matter. Okay? And the BRST symmetry that I'm talking about is simply an encoding of this freedom to move things up and down at the top for the last operator. Any other operator doesn't have this freedom because it's obstructed by other operators in the time ordering. So if there was some other operator here, you can't push it through to the left, to the right, because there might be some other operator in your way. But whatever is at the rightmost, that can be put either up or down. Okay? So that's something that is very well known. It's very well known, not quite in Schwinger-Keldysh language, but it's very well known in the context of scattering theory. This is what was used by Weltmann to try to understand how scattering equations work and to prove unitarity of Yang-Mills theory. This is called largest time equation in that context. Okay? Is this part clear? Because the next slide is going to be significantly more complicated than what I've just said. Okay, so now let me just take these statements and put them into equations. So I'm just going to assert the following, and you can just then you can post facto check that it works. That if there was a BRST complex, if there was a charge, a Grassmann odd charge that squared to 0, it was nilpotent, under which annihilated both which annihilated the difference operator, then it immediately, and if this charge was a symmetry of your theory, then it immediately follows that the difference operator correlator is 0. Therefore, I'm going to say that exist two charges for CPT reasons, Q, Sk, and Q bar Sk with the CPT conjugates of each other, which are such that the O difference is either Q of something or Q bar of something. Okay? Now forget this line, just it's much easier to just read this diamond. What this says is that there is a complex where you can arrive at this difference operator either by taking something which is Grassmann odd and acting on it with the Grassmann odd operator QSK, or taking something else and acting on it with Q bar Sk. Okay? The BRST charges are exactly the BRST charges in Yang-Mills theory, except that nil which you are familiar with, and they're just nilpotent here, and this statement is all we care about. Okay, the difference operator is BRST exact, and these charges are nilpotent. So at some level it seems like I'm doing too much, because I have only one physical theory, one set of operator algebras. In implementing the Schwinger-Keldysh construction, I already doubled my operator algebra by giving them labels left and right. Now I'm telling you, don't stop there. Give them to take the operator algebra and associate with every operator a Grassmann partner with ghost number +1, a Grassmann partner with ghost number -1, and give them labels. So if you have an operator O, let OG be its Grassmann partner with ghost number +1, and OG bar be a Grassmann object with Grassmann its partner with Grassmann number -1, a ghost number -1, such that there's a descent relation that takes you from an operator to its ghost partner by acting with a Q, and a second descent relation when you act on it with a Q bar and you go back to the difference operator. And this complex closes. Okay? So it looks very much at some level, and you will see this later, it will look very much like an n equals 1 Carnot multiplet in 4 dimensions, but it's very important to realize that these Grassmann charges don't carry any space-time labels. They're just Grassmann charges, and they have no other symmetries on them. There's no tensor structure. Okay? If this statement is true, then it immediately follows that the difference operator correlators are 0. Now you might say, well, sounds ridiculous. Why am I doing this? The reason I'm doing this is that it's much easier, as you will see later, to implement this BRST symmetry in an effective field theory explicitly. And by implementing this BRST symmetry explicitly in my effective field theory, I'm guaranteeing you unitarity ab initio. Okay? I don't have to then answer to the question, are you writing down admissible influence functionals? The answer is of course yes, because they're all consistent with unitarity. Yeah?
I'm sorry, I don't know much about the BRST, but BRST is usually associated with gauge symmetry, right?
Not necessarily. Yes, in the BRST discovered their symmetry in the context of gauge symmetry, but it's not necessarily associated with gauge symmetry. Just think of it as topological nilpotent algebra. In all contexts that you probably are familiar with, it's a gauge symmetry, but in this case, it's just a topological symmetry.
I mean, it's just a left to right symmetry, right?
It's not a left-right symmetry, no. No. There will be another gauge symmetry, so don't get confused. Well, let me just say it this way. The Schwinger-Keldysh construction implies the existence of a charge built with an object which squares to 0. Q is an object that squares to 0. It acts on the Schwinger-Keldysh observables. So forget the words BRST if that confuses you. Yeah. Okay. Very good. So I'll try to simplify this in a second. Actually, it's a fun and amusing exercise to do this directly. You can do this at the level of operators, as I said, but you can also take any theory, like say in quantum mechanics, which is simple enough to implement, and implement this explicitly at the level of the Hilbert space, so that you can actually take the Schwinger-Keldysh theory, write down the states density matrix in a double Hilbert space, and then write these operators suitably by extending a Hilbert space to include these ghost objects, and then check how all the identities work. So this is done in one of the references which I splashed at the beginning of the lectures. But I was going to do that, but I think I won't have time to do it, so I'll refer you to the paper. Okay. Now so if all someone told you was you had a Schwinger-Keldysh theory with some arbitrary initial state, this is as far as you go. Okay? So this is as far as you go, and you have these nilpotent charges that you can go to town with, but they give you some constraints, but they don't give you enough power to constrain the low energy dynamics. Okay? They give you some power, but I'm not convinced they give you everything. So I'm going to tell you one more piece of data which at least allowed us to solve the problem for hydrodynamics. And then maybe a comment later on what might be necessary to solve the problem more generally, something that's related to what Tatsuma just said. Okay, So now let's prepare our system in a thermal density matrix. Okay, so our density matrix is e to the minus beta h, and if you have charges, there's some chemical potential times the charges. And now our system is thermal, so the correlation, so suppose you are doing equilibrium, right? If you are doing equilibrium, then you could just forget about the Schwinger-Keldysh construction, and all the Euclidean correlation functions are computed by doing statistical mechanics, by forgetting about Lorentzian time and imagining time being compactified along a circle of period beta. And if you have charges, the charge fields have non-trivial monodromy as you go along that circle. Okay, they have twisted boundary conditions. So if you then compute the partition function, you would get the trace of the density matrix, which of course gives you the thermal partition function. Okay, and this is the gadget that you'll be computing. I'll make one comment, which I didn't put in the slides, that it's often traditional to compute thermal correlation functions in what's called the thermophile double formalism, where instead of computing what I just wrote down, you would compute, you write rho to the half, u left, dagger, rho to the half. In pictures, that would amount to starting with, it will look very similar, except that now these Euclidean excursions are both of size beta over 2. Whereas in my picture, this Euclidean excursion is of size epsilon, and this is almost beta after you take out the epsilon. Now, this is convenient for many purposes, but it obscures one thing. It obscures unitarity. Because if you set the sources in the unitaries to be the same here, unless you know something about the density matrix, or you assume some analyticity properties, you're not passing the unitaries through. Unitarity doesn't follow simply from cyclicity of trace. Okay? Okay. So usually, we'll work with this because we've already captured the essence of unitarity in terms of this piece of the Schwinger-Keldysh BRST currents, BRST charges. When you have a thermal density matrix, we saw yesterday this KMS condition, which told us that there's a certain analyticity properties of correlation functions in Euclidean time. In particular, the right statement is the correlation functions are analytic in this half strip. Okay? It actually means something quite interesting. So let's take an operator, let's take the left operators and shift their time argument by I beta. So in other words, move them down in the complex time plane by I beta. If you do that, and you prepare your system in a thermal state, it's not a hard exercise, you can check this yourself, is that there's a new sum rule. Previously, you saw that correlation function of difference operators was 0. Now you see that if you take the Schwinger-Keldysh time ordered correlator of a right operator at time t minus a left operator at time t minus I beta, and a string of such operators at different times, their correlation function also is 0. Okay, I won't prove this for you. This is a statement that you can find in most thermal field theory discussions, and it follows quite quickly if you just go back to pictures and move things around by. There's a way to think about this, which I'll show you in a second. But you see, this statement looks very much like our previous statement, but it involves some non-trivial action. Our previous statement was simply the fact that you could sort of turn on, doing nothing was related to a topological symmetry. Now, it's saying that in the thermal state, there's another way of doing nothing, and that gives you something else as well. Okay, so and roughly speaking, you've played the game once, you should play the game again, because this tells you that there must be another set of BRST charges associated with this construction.
Can I say something?
Yeah.
You have this kind of songdo in the real time or the complex?
In the real time. Well, no. So in the real time, assuming that the operators here, the right operators are always in the real time, but the left operators, they have a tilde. I don't know if you can see it very clearly, but the tilde means that the left operators are t minus I beta.
How about the default condition is working on this kind of conditions?
Yes. So there will be a second nilpotency condition on these guys. Yeah. So I'll write that in the next slide. So that I'll show you what charges you get.
How about the history? I mean, you have just the macroscope behavior and this kind of things.
Yes.
Purely the randomness you can get.
Well, right now this is still at the microscopic level.
I understand in the imaginary time, but the real time you'd get some problem, I think.
No, I don't think so. Well, okay. There are two different ways of doing this. So traditionally, this identity is derived, but I'll tell you how the identity is derived, and then you'll see why this is just true. Let me go back here. The way this identity is derived, the previous identity was derived by using this as an abacus going down this way.
Oh, yes, okay, that's why. Okay.
Now the identity is derived by going around here.
Okay.
Okay. You can slide operators through the density matrix and back out.
Problem sometimes you would get a non-compactness in the original direction. You would get some problem on this kind of thing.
What original direction? What non-compact?
USS boundary of the initial state and final you can.
No, but the initial state is given to me by thermal. It's only true. My statement is only true for a properly defined thermal Gibbs state.
Okay, I see.
Yeah.
Okay. No, that kind of thing. Okay.
Yeah. Which is why I said that this condition will not be enough in general. In the thermal case, the thermal density matrix is nice enough that there is a condition. For more general statements, I'll just make a vague comment once I'm done with this. Okay, so there are many ways to write this. Don't worry about this advanced retarded. The advanced retarded is just another basis for a second. What I want you to pay attention to is this little operator delta beta, which acts like a imaginary time translation. Because these relations come from viewing this abacus with the imaginary time circle put in on the back, it also follows that there is another condition. Not only are all correlation functions of such operators 0, of these retarded operators 0, but it also follows that you can't have a retarded operator in the far past. You can't have it next to the density matrix, because then you can try to move it back to the density matrix and you get 0. Okay? So, for my purposes, I'm just going to try to do the following. I'm going to again assert that there is a BRST charge, a pair of BRST charges, if you will, for this word identity. Okay? You've done it once, you can do it again, and we just call them the QKMS because they're coming because of the fact that you have a thermal density matrix and are associated with the KMS condition. Okay? So, in other words, given some operator, you have the same complex. Labels have changed because now the bottom component, what is BRST exact, is not the difference operator, but the difference operator where the left piece has been shifted by, whose time argument has been shifted by I beta. Okay? Now, the previous discussion was very, very straightforward because I just moved labels on my operators, right and left got swapped. But I didn't change the time argument. Now, the time argument of one of the operators is non-local in imaginary time with respect to the first, right? Because it's t minus I beta. So these BRST charges are not local in a simple sense. Okay? If beta is, if temperature is finite and the thermal circle is of finite size, these operators are not something that one is usually used to working with. I'm going to, for the moment, I'm just going to formally analyze what this means. And later on, I'll only work in a limit where the thermal circle is small, where I can do infinitesimal transformations. Okay, I'll also make an approximation later, but just remember this in what follows. I've also introduced this gadget, delta beta, capital delta beta, which eventually will become a Lie derivative in the thermal direction, because what it's doing is measuring the difference from between an operator between 1 and the action of e to the minus I delta small beta, which just says it's O of t minus O of t minus I beta. Okay, so if beta is small, this is like a beta times d by dt, and beta times d by dt in a continuum and in the limit we're interested in will become the Lie derivative along the beta vector. Okay, so let me write that down here. So that you can keep track of my symbols as we go along. So this will be the Lie derivative along the thermal vector. And I insist it's not a thermal translation, it's a thermal diffeomorphism. It's really a Lie derivative because these operators could have non-trivial Lorentz labels, which I have suppressed. Okay. So what we have, so just by trying to encode the data of the word identities, we've argued for, we have not derived, I insist, a set of BRST charges, CPT conjugate set of BRST charges for the Schwinger-Keldysh guy, QSK and QBarSK, which were nilpotent, and a set of BRST charges QKMS and QBar KMS, which are also CPT conjugate for implementing the KMS conditions. These 4 charges are nilpotent, so all these Qs square to 0. But no one told us that the QSK and the QKMS must anti-commute to 0. We actually have to compute their anti-commutator. So ignoring this non-locality, let's go ahead and compute. So if you go ahead and compute, so ignore the second part of the slide, you will find that all these 4 charges square to 0. And if you take a Q with a Q, whether it's or a Q bar with a Q bar, you'll get 0, and it better happen that way because the Q's have ghost number +1, and the Q bars have ghost number -1. The ghost number conservation tells you that this line is also obvious. But a Q and a Q bar of different kinds don't have to give you 0 because they have 0 ghost number. And there's a computation to do, and if you do the computation, you'll see that you will find that the commutator or anti-commutator in this case is given by this lead rank. Yeah?
Are there 1 or 2 ghost numbers?
There's one conserved ghost number charge, and all the Q's for me have ghost number +1, and the Q bars have ghost number -1. Thanks. Now, so there was a reason we cooked this up this way, because a version of this algebra, which I'll show you in a second, is very, very well known. And this algebra goes back to these folks. And the way they discovered it was not by trying to think of Schwinger-Keldysh or thermal theories, but rather Van Betten discovered this algebra by taking n equals for super Young-Mills and topologically twisting. Okay? Yeah?
I still have, I don't understand what you are doing. So the fact that you have BRST symmetry implies that you have some redundancy in the system, right?
Correct.
Okay, so it means that your LR system has, when you begin it, when you start it, there was some redundancy already.
That's right.
So what is it?
The fact that you can move your operator the very far to top and bottom. My sliding rule. That's what gave you the fact that the difference operator correlates with 0. See, you're completely right. I think that's right. Indeed, the right way to think about it. This identity came precisely because of that fact. That was the extra redundancy by doubling. So you have to factor that out. And likewise, in the thermal case, there's another redundancy. I'm just encoding both redundancies in these topological charts.
Previous time you talk about this world volume.
Yeah.
And is it also connected to this Schwinger-Keldysh with the world volume theory? And
We will put them all on the world volume in a while. Probably not today. But you will see if I get to what I want to get to at the end of today, you will see a baby version of the world volume. Okay. So the punchline I want you to take away is the following. So there are some redundancies in the description, but importantly, these redundancies imply some word identities at the microscopic level. Okay. All you want to do is find an efficient way to capture those redundancies and those word identities in a fashion in terms of some symmetries. Okay? These BRST symmetries do the job. That's the claim. I mean, if you ask me why, I'll show you how it does the job tomorrow when I actually construct the actions. Okay? But for now, I'm just going to explain what the symmetry is and how to think about the symmetry. Now, this symmetry has too many charges, so I'm going to start with a baby example and show you something that most of you know in differential geometry in a slightly non-standard form, and then show you how to think about this particular symmetry. So this algebra, which I'm going to, is usually called the NT equals to topological algebra, or in some circles the extended equivalent cohomology algebra words. But there's a much simpler algebra which is standard in differential geometry, which is the Vial algebra. So this is some kind of extended Vial algebra. So I'll show you what the Vial algebra is. Any other questions before I go on?
It's practically extended as used in the chain complex.
There is a chain complex, yes.
In the sense of a chain complex, you work out this. Okay.
Yeah. So I have to finish this algebra. This algebra is not complete. I'll finish this in a second. But before I do that, I want to talk about the simpler version of the babier version of this algebra.
So in
Yeah.
this discussion, you don't need a factorization of the two Hilbert space, unlike do you need?
Well,
I mean, in particular, like if you're talking about gauge theory or gravity, and if you repeat the similar theory.
no. So any quantum field theory that you prepare in a thermal state, by just examining the microscopic word identities of trying to compute the real-time correlation functions, at least the Schwinger-Keldysh correlation functions, I claim you can capture all of that in all the relations that those correlation functions will satisfy by imposing the symmetry on that Schwinger-Keldysh path integral.
Okay, but like a Sommerfeld double case, that formulation based on the factorization of the original system and the tilde system. Here you don't you need any?
Well, I'm just confused about what you mean by factorization.
Hilbert space. I mean Hamilton in the.
Well, even here the Hilbert spaces are factorized, right?
So,
because in the contour,
yeah.
the contour has independent evolutions for the right and left.
Then if there is like a gravity, like if there is only gauges, and in the gauge theory, it's hard to think of the factorization or.
No.
No?
I think okay. You're confused about something else. You're right that if you have the two theories living on the same space-time, and you have a gauge field, and you want to split your space-time into two, if you want to split a Cauchy slice into two halves, you can't do it if you have gauge degrees of freedom without imposing some boundary conditions which allow you to split. You have to introduce some super selection sectors. I am not saying that. I'm saying take two copies of space-time.
But in the end,
You will talk about some holography in future, maybe not this.
I haven't said anything about holography.
Okay. I mean.
But if I do talk about holography, then think of them as two sides of the black pearl. In which case, there's no problem with factorization.
Just
Yeah.
I'm sorry to bothering you. Okay, I'm a condensed matter guy.
Yeah.
And, we have been using Schrödinger techniques for free electron system.
Yes.
And we have, say Fermi liquid, and
Yeah.
we have been deriving Dyson equation, Kent equation, and we are all very happy. We never worried about any BRST, any such super topological stuff. We are very happy. And every physical answer came out right.
That's
And,
right, because you have a microscopic
and,
theory, and if you have a microscopic Lagrangian, and you're computing that microscopic Lagrangian, and you're doing perturbation theory, I don't need to say anything. You're completely right. You could just use the standard Schwinger-Keldysh formalism,
yes.
and be happy with it. I'm asking a very different question. I'm asking, how do you do Wilsonian RG if you started with your microscopic stuff and you integrated our degrees of freedom? So if you're using it to compute Kubo formulae,
Yes.
not a problem. But I'm not asking you to compute Kubo formulae. I'm asking you to write down effective actions. So there's a world of difference between what is actually done, and I don't claim to have invented Schwinger-Keldysh. Schwinger-Keldysh invented their story 50 years ago, and it's been very much used in condensed matter and QCD communities to do real calculations. Okay, but all of those assume that you can do perturbation theory. Okay, around some known Lagrangian. Okay. I'm just saying I want to be able to formulate a story where you start with some known Lagrangian, integrate out stuff, and you write down some low energy theory. It may be possible that you write down a low energy theory with some intuition, there's nothing wrong with the hydrodynamic low energy theory that I was talking about the last two lectures. That's written down pretty much with intuition. But there are questions there. Why is there an entropy current with non-negative definite divergence? Okay, I will answer those questions, but in answering those questions, we have to come up with these understand how to think about Schwinger-Keldysh in a much more sophisticated manner than had been thought about before. Okay, so it's not saying that Schwinger-Keldysh doesn't do what it does. It's saying that Schwinger-Keldysh does everything perfectly, but if you want to use it to do low energy dynamics and some kind of RG, you need to capture the information that's already there in the Schwinger-Keldysh functional integral in terms of some new pieces of data. And those new pieces of data are BRST symmetries. Very good. Okay, so maybe this is the place where you'll probably, before I go on, let me to talk about the Vial algebra, let me say this. The statement that I want to make is that the sum rules that people are familiar with in Schwinger-Keldysh that I just flashed for you, they can be captured by this topological charges for this BRST superalgebra, and the advantage of capturing these sum rules into a BRST structure is that topological symmetries are robust under RG. So if I say that the microscopic theory has a topological symmetry, that topological symmetry cannot disappear as I integrate out UV degrees of freedom. So I might as well start by trying to constrain my macroscopic theory, the low energy theory, with these topological symmetries. What do I gain? I gain immediate constraints on influence functions that I didn't have before. Because I'm guaranteeing ab initio that I will keep track of unitarity and I'll keep track of the KMS condition. Okay? So indeed, it will actually do exactly what I'm saying, and it also addresses a major flaw that there is in hydrodynamic effective field theory that we discussed in the last couple of lectures. The macroscopic theory cannot by itself exist with just the pure hydrodynamic degrees of freedom, because those guys know only about response functions. They don't know about the fluctuations that go hand in hand with the response functions. Okay? And an effective field theory should allow you to talk about both the responses and fluctuations, and therefore you need some kind of double set of degrees of freedom. And we will see this explicitly. You will see that there will be a set of classical fields which will capture response and therefore dissipate, and there will be a set of quantum stochastic or fluctuation fields which will be responsible for capturing the KMS condition. And the key question in this way of thinking about it is how are these guys linked to each other? How are the interactions between the classical fields and the quantum stochastic fields linked to each other, and those will be governed by this BRST structure. Okay? So that's the goal, and for us the main reason to do all this was that the moment you say there's a symmetry algebra and the symmetry algebra is topological, you can immediately pass to a superspace, and you can just write down terms. You can write down a one-line Lagrangian which captures all the information. Okay, so there's a mechanical simplicity coming from this whole set of exercises. Of course, the price you pay is a lot of technical details that lie hidden in that final answer. Okay, but baby steps. So now let's talk about something that you all know, and then talk about the full algebra which I'm going to use. So this is a slightly funny slide. I thought about how to rewrite this, but I decided to keep it this way. So imagine for now, forget everything and just go back to standard differential geometry. You have some Riemannian manifold, and on this Riemannian manifold, you have some gauge fields. Okay, and I want to talk about gauge structure on Riemannian manifolds, and this is really what equivariant cohomology is about. It's about cohomology subject to some gauge constraints. That's what equivariance means. Okay, so because you have a Riemannian manifold, you can talk about the space of differential forms in this manifold. You have 0 forms, 1 forms, 2 forms, 3 forms, 4 forms, up to n forms, where n is the dimensional manifold. Now, on the space of differential forms, there are 3 operations. 3 operations you all know and love, but you don't think of them as a super algebra, but they form a super algebra. The simplest one is an exterior derivative, which takes a differential form and increases its rank by 1. Okay. The second one is an operation that takes a differential form and contracts the first index of the differential form, say with a vector, and lowers its rank by 1. So if I give you a distinguished vector, you can always lower the rank of a form by 1 by contraction. Now, given these 2 operations, you can compute. So what distinguishes these 2 operations? The exterior derivative, of course, squares to 0, because you can hit a form with an exterior derivative, but if you hit d squared is 0. Likewise, if you contract a form with a vector, if you contract it twice with the same vector, because the form is antisymmetric, you get 0. So these are like 2 nilpotent charges that are floating around for free. You can compute the anti-commutator, and what I learned in kindergarten, but what some people call Cartan's magic identity, simply says that you get the d derivative when you anti-commute the exterior and the interior contractions. So in some sense, d is like a charge q, I is like a q bar, and L is like a Hamiltonian, like supersymmetric quantum mechanics. Okay, and if you want a physical realization of this, just think of Seiberg-Witten theory that Thomas was going to talk about tomorrow, and topologically twisted, and this is exactly what Witten discovered when he constructed topologically twisted n equals 2 theories 30 years ago. So I'm just going to say this in a slightly funny language here. So imagine you have some kind of gauge potentials. Instead of talking about physical gauge fields, I'll talk about Grassmann odd objects, because I'm going to talk about topological symmetries. And I can define the field strength by the usual relation. So the gauge algebra is given by structure constants f I j k. So this is basically saying dA plus A by j equals f. And df is 0, the Bianchi identity. Okay? So those define for me the gauge structure from the usual Cartan equations. And the interior contractions tell me in which direction I'm doing the gauge transformation, which direction of the Lie algebra I'm doing the gauge transformation. So I'm going to impose this condition on the so if I want to look at cohomology that's invariant under the gauge transformations, I want to sort of ask for forms that are horizontal, that lie on a section, they don't sort of lift off the section. And to do that, I can just pick out my gauge directions and declare my objects to be gauge invariant under that. And you can just compute this whole algebra of these objects once I define D and if I define I, L is defined, and you can just compute the algebra of these guys. Okay, so I squares to 0, D squares to 0, Li gives you back I, Ll gives you back L, L of course follows the Lie algebra, and then Di gives you L as I just said. But this algebra is not an ordinary algebra, it's a graded algebra because there are both commutators and anti-commutators. Okay? So it's a simple example of a cohomology algebra extended by a gauge symmetry, where you have a cohomology generator D, but in addition you have an interior contraction object I, okay, which is also Grassmann OR. So when we give ghost charges, you can think of D having ghost number +1, I as having ghost number -1, and L as having ghost number 0. Okay? So this complex is something called the Vial complex, which is why I call this the Vial model. And we need a generalization of this, which I'm going to talk about next. But perhaps I can pause to ask if people have questions about this algebra, this mathematical fact. Okay? So we want something with two charges, two cohomology generators. Again, this was worked out in prehistoric times, but it's not hard to do. So you'll have two cohomology generators, which I'm going to call D and D bar. They'll have ghost number +-1. They'll both square to 0. Now it turns out, this is the part that's not intuitive and requires a bit of work. There actually are 3 interior contraction operators, not 2. And they form an SL2 algebra themselves. And those are called I's and I bars. Okay? I0, I bar, and I. And then there's one Lie derivation, because all the I's anti-commute with the D's to give you Lie derivatives. So there's 6 generators of this algebra. 2 are the actual cohomology generators. 3 are interior contractions, and 1 is the Lie derivation. We can ascribe ghost number charges +1 to D, -1 to D bar, -1 to I, +1 to I bar, -1 to I, and 0 to I0, and 0 to L. Okay? There's a simpler way to think about this if you want, which is that if you have a D and a D bar, you already have 2 Grassmann directions, because you can vary, you can differentiate in two directions. And then if you have a Lie derivative, then this Lie derivative should either be a bottom or top component of a multiplet, which can be moved in 2 directions, and therefore there must be 3 other generators, which should have ghost number 0, +, -1.
Where is the origin of the 2 generator of the cohomology?
Coming, there will be the Kuhner-Keldysh super BRST symmetries, QSK and QBRST.
That's coming from the line bundle.
Well, there was no line bundle, but in this case, if this was a Kähler manifold, it will come from.
There's a section of
Yeah.
Sorry,
Yeah.
the SL2 is the left hand SL2?
Sorry.
The SL2 is the left hand SL2?
Left shift SL2. Probably. I'm not familiar in that terminology, but.
Well, maybe let me ask you another question then. What's the SL2? Where does the SL2?
Oh, I'm just saying that the I's, the 3 I's transform in the fundamental of an SL2.
Right. So somewhere you have, I mean,
I don't have an intuition of where it comes from.
Okay.
Okay, so I don't want to sort of, so we wrote a long review recasting all of this in terms of trying to recast all of the discussion in many of these papers in some language which was useful for us. But let me just try to sidestep that by passing to superspace where everything becomes much more straightforward. So the problem you're going to have, and I'll tell you what our charges are and what the physical problem is, but bear with me for 5 more minutes when I still go on this mathematical detour. We're going to have two cohomology generators for which I'm going to assign equal and opposite ghost number plus minus 1, and I'm going to capture those directions by two Grassmann odd directions and uplift everything to superspace, where I'm going to give ghost charge plus 1 to theta and ghost charge minus 1 to theta 1. Okay? This is a very simple superspace. It's a two-dimensional superspace with two super directions. I'm just appending two Grassmann numbers at every point in my space-time. Okay? These thetas and theta bars don't have any, as I insisted before, Lorentz labels. So all functions will get uplifted to functions in this superspace. And so if I have functions, so let's say the space-time coordinates are sigma, they will become functions of sigma and theta bar. But theta and theta bar are Grassmann odd, which means that theta squared is 0 and theta bar squared is 0. So any function has a finite Taylor expansion as usual for superfields, and I'm going to use the following notation, hopefully consistently through the rest of the lectures. I'm going to denote superfields with a little circle on top, and the bottom component of superfield will be the same gadget with the circle removed. And the top component will be the same label with the tilde put on top. Okay? And for all intents and purposes, you're only going to have to keep track of the bottom component and the top component, because the top component is going to be the difference field. It's the thing that's obtained by descent in two different directions from F, and the bottom component is going to be the average field in the Schwinger-Keldysh language. So if you like, the way to say everything I just said is that take Schwinger-Keldysh, you had left and right operators, uplift the whole thing to superspace by adding to your theory two Grassmann coordinates theta and theta bar, such that the bottom component of a super operator is the average operator, and the top component of the super operator is the difference operator. And then I guarantee you that any superspace correlator you compute, once you uplift the density matrix correctly, will immediately satisfy the Schwinger-Keldysh word identities. It won't do any more, it will do exactly what's required of it. It's a very simple bookkeeping device to keep track of the Schwinger-Keldysh word identities. Okay, so again, everything is now going to be a superfield, and for our purposes, you can think of bottom components as average fields and top components as difference fields, and you can, as I said, you can forget the intermediate guys for much of the discussion. I'll just keep them floating around for a while, but I'll switch them off later. One feature that I want to highlight, which we will use later, is that the CPT symmetry can be, the difference fields are odd under CPT because right and left get exchanged under CPT if you actually look at the Schwinger-Keldysh path integral. So you can implement CPT by just as an R parity by swapping the two Grassmann coordinates, theta goes to theta bar. Okay. And that will be helpful for some other things I want to say, perhaps tomorrow. Okay? So this slide should be thought of as a rewrite of this slide, just the Schwinger-Keldysh data. Okay? QSK and Q bar SK have become partial theta and partial theta bar and partial theta respectively on this slide. Okay? Any questions? Very good. Now, This is a slightly more complicated discussion, and I don't know how to motivate this more usefully than rely on the mathematical discussion of equivariant cohomology. So let me just say the answer and then see if you guys have questions. So we have the Schwinger-Keldysh BRST symmetry that I've already captured by going to superspace. But there's also what I'm going to call the gauge sector, okay? And this gauge sector is different from the redundancy of the BRST, what I've been calling BRST. There's this gauge sector, and this gauge sector is going to be there to capture the KMS condition. Why is that? You saw in this Vial, in this simpler Vial model, that there was an underlying set of gauge directions that was used to implement the equivariant cohomology. Okay? And so the interior contractions were associated with those guys. Now, while I sort of started out the discussion by saying you have a QSK, Q bar SK, Q KMS, and Q bar KMS, I have to make a decision at some point of which of these are actual cohomology generators and which of these are interior contractions. So it turns out that the Q KMS and Q bar KMS are actually interior contractions, and therefore they must satisfy some gauge algebra because they correspond to some vector fields that are propagating on the Schwinger-Keldysh extended superspace. So I'll tell you what the gauge algebra is in a second. So I want to postpone that, but just say what happens for the moment when you have gauge symmetry in the superspace, and parameterize how to think about the gauge symmetry just abstractly. So imagine you had gauge superfields in a space with two super coordinates. Then your gauge superfield is a one form, but which will uplift the super one form, and therefore it will have a usual one form piece whose coefficient is now a superfield, and then it will have a Grassmann odd form piece and two Grassmann odd form pieces, each of which are themselves superfields. Okay? So remember that these things have circles on them, so these guys have an expansion in theta and theta bar. They have Taylor expansions. This statement here is just saying that when I have tensors, my tensors also can point in the space in the super directions. Once you have this gauge superform, you can of course define gauge covariant derivatives and their field strength the usual way, where you have to sort of, the partial I now runs over partial usual space-time coordinates and over theta and over theta. Okay? So what I want you to keep in mind is that all of this discussion is a clever way of doing cohomology when you have gauge symmetry going along to the right. If you're trying to keep track of structures on a manifold that have some underlying gauge bundle on them and you want invariance with respect to that gauge bundle, this is the way to do it. Okay, and because I have Grassmann odd objects, when I move them around I pick minus signs, and therefore there are Grassmann signs here in this definition of the usual definition of what the field strength is. It's not just it's either a commutator or an anti-commutator depending on what I and j indices mean. If both indices are Grassmann odd, then it's a commutator. It's an anti-commutator. Okay. Now, I thought I'd have time to actually explain how to fill out this multiplet, but let's just do some counting and then fill out the multiplet. So A is a super one form, is a superfield super one form, and therefore it has three form components, each of which are superfields, and each superfield in our world has four components. Because in the theta bar expansion, everything looks like what I just wrote before. Everything has a bottom component, a top component, and two Grassmann odd components in between. So there's a space-time one form which has and four of them, and then there are 8 space-time scalars in the A theta and A theta bar. And by a clever choice, you can do the following. You can parameterize the multiplet in terms of, let me use a mnemonic and say 12 fields. 3 of them are going to be gauge potentials. I mean, I'm after all parameterizing a gauge field, so some of them have to be gauge potentials. So, G and G bar are going to be the bottom components of A theta and A theta bar, and AA is a gauge potential associated with the usual gauge potential. B is a gauge non-invariant object, which you can also think of as a gauge potential, but it's really it involves a derivative on the gauge potential, but it's an independent object. And I've assigned them the right ghost numbers. So A, the bottom component of the gauge field itself has gauge number 0, but G and G bar have ghost number plus minus 1 respectively, and B has ghost number 0. If you like, you can think of these 3 guys as the reason why there are 3 interior contractions. One of the interior contractions knows about G, the other knows about G bar, and the third guy knows about B. Okay, that's where the SL2 comes from. That's one way of seeing the SL2, but this parameterization actually breaks that SL2. In addition, when you take derivatives of the gauge potential, the gauge potential has objects of ghost number plus minus 1. So if you hit it with another derivative, you may get objects with ghost number plus minus 2 or 0. So those guys, these 3 guys, phi 0 and phi bar, are basically the bottom components of 3 different field strengths after using some Bianchi derivatives. Okay, in particular, just I highlight phi 0. It has ghost number 0. It's the bottom component of f theta theta bar. And the etas are ghost number plus minus 1, and they are derivatives of field strengths. And the remainder of the vector multiplier is sort of the standard. It's just the gauginos and the f term, as in usual in vector superfields for 4 dimensions. Okay. Now, what I said before was that we have 2 cohomology generators, D and D bar, which are nilpotent. But anybody who studied gauge symmetries, theories with gauge symmetries, know that it's silly to work with differential operators that are not gauge covariant. Okay? D and D bar are nilpotent, they square to 0, but they're not gauge invariant. So what you can do is you can add D plus A, but D plus A won't be nilpotent because D plus A will give you a field strength. D plus A squared will give you a dA term which will give you a field strength. Okay? So what I'm going to do is I'm going to define what are called Cartan charges in literature by combining my exterior derivatives with interior contractions, and then those guys will give you will square to some lead drag along field strengths. Okay? So just keep this in mind. This will be helpful because that's how I'm going to parameterize the theory, because eventually we're going to write down a gauge invariant theory. And gauge invariant theories are best written in terms of gauge covariant derivatives, but gauge covariant derivatives won't square to 0. Okay, now finally I can tell you what my labels mean. So there was an abstract algebra which I call this NT equals 2 algebra, and I've been sort of talking for the last 15 minutes or so about just abstract mathematics. So what does it have to do with the Schwinger-Keldysh stuff? The cohomology generators of this topological algebra are to be identified with the Schwinger-Keldysh topological charges, QSK and Q bar SK. The 2 interior contractions that have non-zero ghost number should be identified with the KMS, QKMS and Q bar KMS. There was a lead derivative. That lead derivative I'm going to call LKMS. That's going to be this delta beta, this L beta that was there before. And then there's a new interior contraction which is just there for the closure of the algebra. That's another Q0 KMS that you can also have, that you can also infer by just trying to close the algebra that I had before. Okay, so my algebra that I wrote before was not closed. It needed one more generator, and this is the object. So once you have all this structure, the only thing I need to tell you is what gauge symmetry. Okay? Because everything else is algebraic, everything else is some mathematical mumbo jumbo. So what gauge symmetry are we talking about? And the gauge symmetry I'm talking about is one where the lead derivative is this guy. Okay? The lead derivative is a lead drag along the thermal vector. But I already made my complaint earlier that this is a non-local gauge charge because it involves finite translations along the Euclidean thermal circle. So I don't know how to make sense of this in general, but I do know how to make sense of this in a particular context, which is at high temperatures.
For Riemannian case, is there any difference of the change of in algebra?
Sorry, what do you mean by Fermionic case?
For Riemannian case, KMS relation keep the minus sign. And,
Oh, no, okay, so
doesn't
you know, to make my life simple, in the slides I actually took the effort of removing all Grassmann, all my plus minus signs which were there in the KMS relation. So you can go back and read our papers where those signs are kept manifestly or no particular purpose, but nothing really changes. Yeah, you're right, the KMS relation in the Fermionic case will have anti-commutators and commutators. Was there another question? Okay.
I have one more question.
Yeah.
So here,
if you work with the gauge field, I mean your original Lagrangian is given by gauge field, and along the thermal circle you have very could be non-trivial boundary condition, right? If you
No, the gauge field just satisfies the usual boundary condition.
usual boundary condition.
See,
Yeah.
okay, I think what you're getting, there are two things to be careful about. Let's say you're doing QCD and you have real gauge symmetry. All the QCD bosons, including the gluons, are periodic under the thermal symmetry. They obey the standard Bose-Einstein statistics. Nothing funny about them.
some non-trivial twisted boundary.
No, that's for flavor symmetry. That's for flavor symmetry when you have chemical potentials, not for the gauge fields. The gauge fields don't carry flavor symmetry. Yes. So if you have flavor charged objects, they will have twisted boundary conditions.
In that case,
But those can be absorbed into what I'm saying. I just have to define my charges appropriately. So my lead derivative. So what I say by lead derivative here, that lead derivative will also involve a twist by the charged object for charged objects. Okay, I have what 5 minutes, 7 minutes. Okay, very good. I think I can leave you with a punchline that's interesting. Okay. Let me say heuristically about this algebra is because we've tried to derive this and we've not succeeded, and I don't think anybody's derived this algebra, but there's a lot of post facto evidence this algebra is correct, and on this gauge symmetry is correct. So imagine, so the intuition I want you to take away is this. I told you yesterday that if you're in equilibrium, you can think of equilibrium by studying your theory on a Riemannian manifold, where there is a thermal circle fibered over a spatial base. I in fact wrote down the metric yesterday. Now we want to talk about general out of equilibrium problems because we're trying to compute Schwinder-Keldysh correlators. And the way you think about this is that you have your Lorentzian manifold, and as you go along your Lorentzian manifold, at different places you have different values of temperature and local choice of inertial frame. So in other words, your thermal vector switches from place to place. Let me heuristically continue to keep saying that there is a local thermal circle fibration over my Lorentzian manifold, and the claim I want to make is the way you should view in a very heuristic sense everything I just said is that you demand equivariance in the non-equilibrium context too under this thermal circle diffeomorphism. That's what this L beta means. So we are going to impose a gauge symmetry where the gauge algebra is given by this bracket, where two gauge algebra generators have a commutator which is given by a difference of the lead derivations under the, and L beta, I remind you, is a lead drag along a vector. So if lambda carries some labels, then lambda will get non-trivially transformed. And the gauge field itself transforms as usual by the bracket up to inhomogeneous. So in some sense, the symmetry we are going to impose for near thermal systems is the symmetry of diffeomorphisms along the thermal circle. Inspiration for doing this comes from knowledge of equilibriums, where we already saw that diffeomorphisms around the equilibrium thermal circle gave you entropy. And in some sense, you will see that diffeomorphism, this gauge field is going to couple to entropy. So somebody was asking me about whether there is the symmetry principle associated with entropy, and that symmetry principle is the thermal equivariance. Okay, I think I'll skip this. I think I've said enough about these KMS charges, and let me make 2 comments and then end. So the algebra that eventually we will work with is a theory where you have 2 cohomology generators, covariant cohomology generators under this thermal algebra, where the Q squares to L beta, Q bar squares to L beta up to a field strength, and Q bar is also a field strength. And remember that these field strengths carry ghost number, because Q carries ghost number plus 1, so this carries ghost number plus 2, this carries ghost number minus 2, but this commutator, anti-commutator, has a right hand side that carries no ghost number. Okay? So you can check this explicitly, and there's a philosophical difference which I wanted to highlight between our way of thinking and some other groups that have tried to do this, in particular the MIT group of Paulo Glorioso, Hong Liu and Crossley. The philosophical difference is the following. They like to say that BRST, Inchfinger Keldy, should only be imposed by a single generator, not CPT conjugate pair of generators. And the KMS condition, for them, the words they use, is that it gives an emergent second generator which combines with this delta to give you this algebra. So they would write down this algebra, forget this for a second. So they would have a delta and a delta bar that square to 0, and a delta bar anti-commutator that gives you a tanh factor. Okay, I can explain why the tanh factor comes from. The tanh factor comes from Bose-Einstein statistics. Okay, just comes from the KMS solution. Now, if you take our algebra, which is in some sense larger because it has full equivariant symmetry and it has a gauge symmetry, and if you set f theta bar, f theta to 0, and f theta bar theta to a particular value, then you'll agree with that algebra in the high temperature region.
So the other group,
yeah,
do they assume the temperature is
Or same in the.
No, they don't. Well, they don't, but they write down this action. You should ask them what they mean.
Okay, beta depends on some space time.
Yeah. Okay. Now, once you come here to this line and you approximate their algebra by this statement here, this algebra is not new. This algebra is actually very, very well known, and I claim it actually dates back 45 years to a very influential paper by Martin C. and Rose. But it's very well known in the context of statistical mechanics and stochastic dynamics, which I was going to end on, but I think I will postpone that till tomorrow. So let me stop here.
Okay, thank you. Okay, you have the delta B, represent 1 minus exponential y delta. That's the bulk is about coming from boundary. You mentioned about that. Is it that's the origin of the that's line of the some formulas?
Sorry, say again, please.
That's what is the origin of the delta B? That's the some kind of origin the formula on this the fibers. You have the some kind of section.
Well, okay. So if you want to think in the fibration language, what you can think of delta B doing, it moves you up and down the circle.
Yes.
Okay.
Yeah.
And what I'm saying is that if you think of the thermal circle fibration over your manifold,
right,
all sections should be equivalent.
Average of the, and then just you have some kind of the emerging of the formula. This is some kind of the fiber and.
Well, I think it gives you gauge symmetry. It doesn't give you fermions. The fermions
it doesn't matter. Okay.
Yeah, it gives, the fermions come from the BRST structure.
Okay.
Yeah. I mean, I won't even call them fermions because it's a bit confusing, you just call them ghosts. Because the
Okay.
graph-
Yeah,
graph
I
is
understand
odd.
that point. Okay.
Yeah.
So, any other question? Okay, I think we have lots of questions already in the talk. So let's thank Mukta again.